Now that we've seen the validity of the trajectory equations when a projectile is launched from a tower, let's try to solve a problem where we can make use of these equations. We have a projectile that is launched from a tower of height 100 meters with a speed of 70 meters per second, making an angle of 30 degrees with the horizontal. We are asked to find the vertical displacement from the top of the tower when the x displacement is 300 meters. This is a case where we are given the x displacement and we need to find the y displacement. So using the trajectory equation, we can make life easy for ourselves. This is the full trajectory, right from the time it is launched to the time that the projectile lands. And we have to find the vertical height above the horizontal reference line AB when the x displacement is 300 meters. If we plug the given values into the first form of the trajectory equation, that is, we substitute 300 for x, 30 degrees for theta, 70 for V0 and 10 for G, then we obtain the y displacement as 50.77 meters. Now this is positive, meaning it is above the reference line AB. So when x is 300, y is 50.77 above the reference line which passes through the launch point A. If we needed to find the y displacement from the ground, it would be the tower height h, which is 100, plus y, which is 50.77. So from the ground, the y displacement would be 150.77 meters. If you try substituting these values into the third form of the equation, the y displacement we would get would be identical. Now let's solve this for another value of x. This time we compute the y displacement when the x displacement is 520 meters. Again, if we plug the given values into the first form of the trajectory equation, that is, we substitute 520 for x this time, 30 degrees for theta, 70 for V0 and 10 for G, then we obtain the y displacement as minus 67.65 meters. This is negative, meaning this is below the reference line AB, so y is negative here. Now the y displacement from the ground would be the tower height h, or 100, minus y. So from the ground, this would be 100 minus 67.65, which is 32.35 meters. And had we solved this using the third form of the trajectory equation, the y displacement would have been the same, would have been minus 67.65 meters. Now using the second form is something we need to be careful about. So let's try and solve this very same problem using the second form of the trajectory equation. All you have to remember is that when you're using this form of the equation, the range in the equation refers to the distance when we get back to the same horizontal level as the launch point A. So our range is RAB for which we have a ready formula, which is v0 squared times sine of 2 theta over g, and this gives us the range as 424.39 meters. Now this is the range that we will substitute into the second form of the trajectory equation. So let's do that next. So in the second form of the equation, we substitute 520 for x, 30 degrees for theta, 424.39 for the range RAB. Remember, it refers to the distance AB. And we arrive at exactly the same y displacement, which is minus 67.65, when the x displacement is 520 meters. Again, if we want the y displacement from the ground, it would be the tower height h, which is 100, minus y, so this would be 32.35 meters. So we can safely apply the trajectory equations for the launch of a projectile from the top of a tower. These equations are valid if the launch is from the ground or it's from a tower. The trajectory equations are valid when the projectile is launched from a tower. These trajectory equations are valid throughout the flight of the projectile, right from the launch point to the landing point.